it's a beautiful day. Sky falls, you feel like it's a beautiful day. So let it get away on the road.
All right. Hello, it's Mr. Kelly again, and we're getting ready to start with our next presentation. And I'm going to try an outdoor setting for this one. Such a nice day today. All right, so you may hear some airplanes going by or some lawnmowers, but worth it in my opinion. All right, so circular motion is the topic for today, and you know some things about circular motion already, or things that move around in a circle. So one of the things that you know is that the distance around a circle is called the, of course, circumference. So that's a good word to start off with here, and there it is up on the screen. All right, so we're going to be doing calculations, and the calculation, the distance around a circle here, or the distance that is the circumference of the circle, is 2 pi r. So 2 pi r, where r is the radius of the circle, gives you the distance around the circle. Very interesting discoveries that were made with circles way back when, and even more interesting, the applications. Remember, as we go through this topic, like with all topics, you should be thinking of the applications. I'll give you the basics, but be thinking all along, where could I go with this? Okay, so we know already that speed is the distance that you cover divided by the time, so it should make perfect sense that in going around a circle, the speed would be 2 pi r, that distance, divided by t, if we define t as being the time to go around the circle one time. So the time to go around a circle one time has a name to it, and that name is the period. So the capital letter T is used to represent the period of an object moving around a circle. Okay, so how about this one? Give this a shot, and I'll pause as usual and see how you do with this problem here. Give it a try. All right, I'm back. Did you get this as your answer? Hey, if not, bring the questions into class. This can be complicated stuff, that's for sure. Okay, let's give a few more a try here, just to see if you got it. This one involves a little bit of a wrinkle. See if you know what it is, and I'll be back in a minute. Okay, we're back, right? Yeah, this time, of course, you had to make the conversion from kilometers to meters to get the correct answer, but you should have come up with 44.9 seconds. How did it work out? Bring your questions to class, please, as always. Okay, so this is the time per cycle. Cycle is another word for the time around a circle. That's the period. And if we were talking about how many cycles in a given time period, we talk a lot about cycles per second these days. That is the frequency. So the lower letter f, lowercase letter f, is used to indicate the frequency, where the capital T is the period. These are, of course, inverses of each other. The frequency, you may have been heard, is measured in hertz or inverse seconds. If the period is in seconds, then inverse seconds would be the unit for the frequency. If the time unit is seconds, of course. Okay, so here, just to indicate that they're inverses, there's a way of representing it anyway, symbolically. Okay, so how about it? What is the frequency of the motion in the previous problem? You know, your x to the minus 1 key works very well for these types of applications, but you should have gotten an answer like this one. And again, if you don't, bring your questions to class. That's a great idea. Okay. So, what does this even matter? Like I'm always asking you, take it a few steps further. What does this matter for circular motion? Well, you can start taking circular motion and then thinking about what happens when you have an oval. This is a circular track, but most tracks that we look at would be ovals. So elliptical, if you will. So how would we take circles and stretch them out to ellipses? That's a pretty good question to be asking. Or maybe something that is round can tell us some things. Maybe we can know the revolutions per minute for a car, and maybe that could be used to figure out its speed. But these are only some basic applications. Start thinking about other ones. How could this be applied to the real world? That's the most important part about the class anyway, in my opinion. Okay, so our solar system is also elliptical patterns, and circular motion gives us an estimate of what's going on out there, and that's how we started understanding the solar system. And pretty interesting stuff that people have pondered for years and years, and where we have taken this and where we will take it is pretty amazing. Human beings pretty smart and able to accomplish some amazing things, and I think we're only just beginning. And here you are, the next generation, to take it a little bit further than the generation before. It's kind of exciting. Okay, so let's get back to Earth and then go back to the Moon. How about it? Let's say it was a circular orbit, the Moon around the Earth. It's not exactly, but let's make an estimate here given this information. So there's the information about the radius of its orbit from us and its period in days. So let's ask some questions. What would be the speed of the Moon in meters per second? What would it be? Give that a try. When you come back, I'll give you the answer. Hey, welcome back. I came up with that as an answer. That's pretty good. 1,000 meters per second, roughly 2,000 miles per hour that Moon is moving at. Pretty impressive. Doesn't seem like it's moving all that fast from our perspective. All right, well, how about in miles per hour? Since meters per second doesn't mean all that much to us, I give you a rough estimate. 1610 meters per mile. That's a little bit off. It's probably about 1609, but it'll give us a rough idea of what's going on in miles per hour. And when you come back, I'll give you the answer. All right, well, there it is. And like I said, roughly 2,000 miles per hour, but now we have a little bit closer to the real answer. Okay. Okay, so there we go, and moving on. All right, centripetal acceleration then is the next thing that I want to talk about. When you are accelerating, it means your speed or your velocity is changing. So for centripetal acceleration, we'll take this formula on faith for the moment. It's the speed squared divided by the r, the radius of the motion. So there's centripetal acceleration, and here's the definition of those variables. Okay, so that's our centripetal acceleration and the variables in representing it. So how about this? If you were moving in a circle at a constant speed, how can you be accelerating, right? Your speed isn't changing. But remember, it's velocity that we're talking about. So even if it's the speed staying the same, the direction is constantly changing. And that's why we can say that it's always accelerating, centripetal acceleration. An acceleration always changing the direction toward the center of the circle of motion. Okay, so let's try a problem with that one. I'll pause and come back to you in a moment. And we're back. Okay, you should have had this as your answer and bring your questions to class. If you don't, we'll try a couple more quick ones here. All right, well, there's the answer. What's the question? All right, give this one a try and see how that works out. And see if you get that answer. This time you don't even have to wait to see what the answer is going to be. But why don't you pause, see if you get that answer, and come on back again. All right, welcome back, and here's another one for you to try. Let's see if this works out for you. Give that one a try. And pause, and I'll come back with the answer. And here it is. There you go. So the speed and then the acceleration. So using some other formulas to find the speed and then the acceleration. Okay, so here's another one for you. Pause, come back. You know the drill by now. And you're back. And there's the answer. And bring your questions to class, please. All right. And here we have another one where I'm asking you to give it in hours. This is getting to the point of what a planet might be like. This is a planet, not exactly the Earth, though. What would its period be? And there's the answer. Okay. Okay, well, if an object is going in a circle and it's accelerating, there has to be something causing it to do that. And we already have from Newton's second law the idea of centripetal force. So now what we're going to do is apply Newton's second law to circular motion with centripetal force. For a car moving in a circle, it's going to be friction that's moving it in a circle. There's got to be something that supplies the force, something besides just saying the centripetal force. Get used to saying the centripetal force is caused by, or something like that. If we were taking an object and spinning it in a circle on the end of a string, then it would be the tension in the string that would be causing that centripetal force, the pull on the object. And how about for planets going around a sun, or a moon going around the Earth? Well, Newton figured it out a long time ago by looking at the apple falling from the tree, but it turns out that it's gravity that supplies the centripetal force. And I can see the words centripetal force are cut off there, but it's the gravity that supplies the centripetal force. And that should make some sense to us now, although it was new in Newton's day. Just like Newton took it a little bit further and thought about different ways things could be applied, I'm going to keep encouraging you to do that. That's where all the advancements come in anyway. Teach you the basics. All right, so we know that Newton's second law is F is equal to ma, and now that we have a term for centripetal force, or centripetal acceleration, I can say, we also have a term for centripetal force, and that should make some sense too. Okay, now already you might be thinking about the idea of friction for a car going in a circle. That's a pretty good thing to be thinking about. Okay, a little quick editing here. Sorry that video went a little longer than I had wanted it to, but that does it for this video. Thank you for watching, and I look forward to seeing you back in class.
It's a beautiful day.